Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Our lesson today deals with quantities in chemical reactions, and it starts on page 173 and it ends on page 177 from the text Chemistry 11 in Focus. And we'll be introducing stoichiometry and doing calculations involving mass-to-mass relationships of reactants. Once in a certain country, during tough economic times, there was a chronic shortage of basic household commodities, including soap. A poor woman was told that if she boiled the fat from her slaughtered pig with sodium hydroxide, it will make her some soap. She did this and obtained some soap. However, when she bathed her children with the soap, they suffered severe skin burns and had to be hospitalized. The above scenario exemplifies what happens when reagents are not mixed in correct quantities during chemical reactions. In this example, pig fat reacted with a caustic solution of sodium hydroxide, neutralizing some of it and forming some soap and glycerol in the process. But because the quantities of fat and sodium hydroxide were not accurately measured and mixed, after the reaction, some sodium hydroxide was left in excess and it caused skin burns. In chemical reactions, the reactants have physical and chemical properties which are different from the products they form. In this case, sodium hydroxide is extremely toxic and dangerous, but the fat is greasy and harmless. The soap formed is safe to use for cleaning and bathing, and the glycerol, a byproduct, is a safe alcohol. But if one of the reactants is in excess, it may remain with the product and retain its original properties. This is what happened in the case of sodium hydroxide. Of course, the sodium hydroxide in this case was left in excess, and because of that excess, retained its caustic property. Had the fat been the excess reagent, it would have neutralized all the sodium hydroxide, but some of it would have been left over. In this case, the soap would have been greasy. Companies that manufacture medicine, drugs, and other types of treatment that people drink or use on their bodies must ensure that no excess reagents are left in their products, as these may cause harm to users. This method of using correct quantities using balanced chemical equations to ensure that there are no leftover reagent encompasses stoichiometry. This concept is further developed as the chapter progresses. So now we're talking about quantities in chemical reactions. We talk about the importance of having balanced chemical equation. So this equation here is showing you how hydrochloric acid is reacting with sodium carbonate. Here you're seeing 2 moles of hydrochloric acid are reacting with 1 mole. You don't see that. When you don't see the 1, it is understood that it is 1. So it is reacting with 1 mole of sodium carbonate to produce 2 moles of sodium chloride, 1 mole of water, and 1 mole of carbon dioxide. In this case, the reactants will disappear and only products will remain. If these are well balanced, you have exactly 2 moles there, and you have exactly 1 mole here, these will react with each other completely, and they'll give you 2 moles of sodium chloride, 1 mole of water, and 1 mole of carbon dioxide there. There will be no excess reactants remaining with the product. So now we can look at some relationships here. What we can say here is this. We can see that every 2 moles of hydrochloric acid requires exactly 1 mole of sodium carbonate to produce simultaneously 2 moles of sodium chloride, 1 mole of water, and 1 mole of carbon dioxide. That's one way of looking at this. You can look at it from the perspective now of sodium carbonate. We can say that 1 mole of sodium carbonate requires 2 moles of hydrochloric acid, and in the process it will produce 2 moles of sodium chloride, 1 mole of water, and 1 mole of carbon dioxide. From the perspective of the products now, one of the products, you can say 2 moles of sodium chloride are produced simultaneously with 1 mole of water and 1 mole of carbon dioxide whenever you have 2 moles of hydrochloric acid react with 1 mole of sodium carbonate. So this will lay the foundation for us to see that there are ratios that exist between the products and the reactants. And we can look at it from the perspective of carbon dioxide too, what we can see. For every 1 mole of this that is produced, 1 mole of this must be produced, 2 moles of that must be produced. And to get that, you must have 2 moles of this and 1 mole of that. You can look at it from different angles, okay? So these are ratios there. Now we can look at it in terms of mass. We can translate those moles into mass. I put in this way to see because sometimes people don't realize what's happening there. So here you have your mole ratio, 2 to 1 to 2 to 1 to 1. If we change these to mass, you get that mass of HCl will require that mass of sodium carbonate, and you'll get these masses of sodium chloride, water, and carbon dioxide, right? So you can establish a relationship again. You can say that every 72.9 grams of HCl needs that 105.99 grams of sodium carbonate for complete reaction, and simultaneously produces, okay, these guys here, that mass of sodium chloride, that mass of water they are seen in the equation, and that mass of carbon dioxide. From the perspective of sodium carbonate now, you can say that that mass of sodium carbonate needs exactly that mass of HCl for complete reaction, and these are simultaneously produced, like we said before, these masses of sodium chloride, water, and carbon dioxide. From the perspective of this, that amount of sodium chloride is produced simultaneously with 80.02 grams of water, 44.01 grams of carbon dioxide, when exactly that amount of HCl and sodium carbonate are reacted. All right, this is for complete reaction. So now you can see these relationships that exist there. This is the introduction to stoichiometry. So now you know in the mole ratio here, you can have given students to do these, right? Every 2 of these, watch me do one for you. Every 2 of these requires 1 here, 1 here, and 1 here. What if you have 4? We're doubling that amount. Huh? Do one for you. If you have 4, what would this be? Every 2 will take 1, every 4 will take 2. And everything will be double. This will be 4. Okay? This is going to be 2. And you're brighter than me in maths, and all 70-year-old man, you can do those things for yourself. Okay? So you practice that. Okay? These are stated in the solution manual. You can see the answers there. Now we'll do a real problem. The gravimetric stoichiometry. So what are you saying? In the previous exercise, there were a number of moles of one reagent was given. It was relatively easy to determine the number of moles of all the others in the equation. We've seen that just now. Just give some practice like that, right? So let's go back to the same reaction here now. And let us say now they didn't give you one of these in moles, but they give you in mass. So look at the problem. They're asking you what mass of HCl is required to neutralize this mass of sodium carbonate. Right? See, they didn't give you moles. If they give you moles, it was easy. So what we do, we try to change this value here from mass to quantity in moles. So we'll follow this example here and hopefully understand how to do these problems. So this is what is called the provided quantity, that mass, and this is what is required, okay? It's just showing you why you can't use mass. Look, if I have, according to this equation here, right, this is the amount of sodium carbonate, and that is the amount of HCl that's used to neutralize it. So if you have 26.5 grams here, you can't just say it's 26.5 grams here, okay? Because these are not the same. If they was the same, then you'll say this will be exactly the same as that. So what we do is this. We change sodium carbonate from mass to number of moles. So you do that, you find the molar mass of sodium carbonate. You have to find that, which is this, 105.99 grams per mole. And you divide this by that. So you can see I have a small quantity here, which is this, okay? And this here is a molar mass here, okay? And of course, we have spoken about this guy here. We use that here to find number of moles is equal to mass divided by molar mass. So don't forget to use the triangles, okay? And it turned out to be 0.2500 mole of sodium carbonate. Every one of sodium carbonate here requires 2 of that. And we get this. How many moles do you think you'll need here? 1 to 2. If it says 0.5 moles, then you're good. So what we'll do is this. You want to find how many moles of HCl first are required to react with that number of moles of sodium carbonate. If you know the number of moles of this, then it's easy to find the mass because you can use that triangle there and you'll see. So what we'll say is this. Watch this now. They introduce something new to you. Because you just calculated this guy here, we'll call that the given reagent. And of course, this was the required reagent here. So this mole ratio is 1 mole to 2 moles. So if you have 0.2500, you should know what this should be. If it says 0.5, then you're right. But we don't guess it like that. There's a way that we establish that. So watch this now. We will write an equation like this. We put given over required. Watch. Given. This is the given guy. Okay. And this is what is required. And you put now their number of moles as represented in the equation here, balance equation, against them. So in the given in this case is 1 mole. And what is required here is 2 moles. So if the given, the ratio is 1 to 2. Now that you know this guy here, put it where the given is 0.02500 moles of sodium carbonate. And let this be X. You don't know how much of this HCl we're going to use. Now you use this relationship here, all right, to calculate what X is. You know more mass than me. You cross multiply here. So you get 1x, should be 1x, doesn't matter as long as you see x on. And you see what? Remember we say it's going to turn out to be that guy? Alright? So you need 0.500 mole. Now what is the mass of this? You use this one here. Mass is equal to the number of moles, then the molar mass. So in this case, the mass of the HCl will be equal to, that's the number of moles we just calculated, then the molar mass of HCl, which is equal to that. And this is what you're going to get. So I said the method of using mole ratios to calculate mass of one reagent, which is then used to calculate others in a reaction, is called gravimetric stoichiometry. Now, we're asking about this guy now. What mass of this is required to react with that mass of HCl? Which is provided and which is required. This is what is required now, okay? This is what is required. And the other one is provided. Again, you have a perfectly balanced equation for the reaction. And you are given this guy here. I'm showing you here. how this mass here is different from this mass. So if you're given this, you just can't say it's the same as this, right? Because it wouldn't work out to be the same. So we do like what we did before. Find is the number of moles of the given one. So in this case, it's HCl. This is the mass given, and this is the mass of the HCl here, molar mass, and it works out to 0.2 mole of HCl. So this is 2 moles here, requiring 1 mole here. We have 0.25 here. What do you think this should be? What do you think that should be? Yes? 2 to 1. This is, if you say 0.125, then you're right. Now you establish your mole ratio on that equation now. You can put that in your equation. This is given, and this is what is required, okay? Well, we just found what is given there. Of course, should be half of that. Well, there's a way of doing that. Given, and you can see the given there is 2 moles. The ratio here is 2 moles, and that is, the required is 1 mole. Be careful with those things, okay? And this, you just calculated this, that's given, and you find for x. Now when you cross multiply, you're getting 2x, okay? And this is the one we figure out mentally just now, okay? You need 0.125 moles of sodium carbonate, right? And now you can find the mass of that. Mass is equal to number of moles times molar mass. You're given the formula here, and you translate into that one there. If you do that, we taught you how to do that already, all right? And that's the mass of sodium carbonate that is used to react. Quick review of that. You'll be given a certain mass of one reagent, and asked to find the mass of the other reagent that is required to react with it. The first thing you do is to find the number of moles of that reagent here. In this case, it is 26.5 grams of sodium carbonate, and you want to find the mass of HCl that is required. You can't use mass. You have to change into moles and use the mole ratio, and then you change moles back into mass. So here is a balance equation here, 2 to 1. Now, this is the mass of the sodium carbonate. Change that to moles. So if you know the number of moles here, you can know number of moles here because of this 2 to 1 ratio here. So we do that. Take the mass, divide by molar mass. So number of moles equal to mass here, divide by molar mass. See, small quantity divided by this. You get that number of moles of sodium carbonate. Now you know this number of moles here. Because you know this mole ratio here, you go and find number of moles of your HCl. You establish a relationship based on the balance equation. That's 1 mole of this takes 2 moles of that. So you know this. You want to know what that is. Let that be x. This is given. The one that you just calculate, the one that's required, is unknown. Establish a mole ratio here. 1 to 2. You have x at the bottom, you cross multiply, and you get that number of moles of HCl. And you now use this equation here to find the mass of that by multiplying the number of moles by the molar mass of that. And that is how you do these problems. I don't know why I didn't give some example to do. Next lesson you find lots of this.